Does anybody need more time here? So here's some definitions for each of those. The intermediate was the substance formed briefly during the reaction, but then it was quickly consumed to form the product. It's not present at the beginning and it's not present at the end. It's just temporary in the middle of the reaction. It's there. The catalyst, we know they speed up reactions. They don't undergo any permanent changes because they get spit out of the reaction just like they were there when it started. So they are present at the beginning and they are present at the end. We've got an energy profile here. This must have been an exothermic reaction because it started off with medium potential energy. At the very end, we're down to lower potential energy, so it must have released some of its energy. The uncatalyzed reaction is shown with the red graph. It's got a really high hump to go over. If you add a catalyst, it pulls that activation energy barrier down so it doesn't take quite as much energy to overcome the activation energy barrier. How it does that, that's what we call a mechanism. How it does that is by somehow stabilizing the reaction intermediate. It makes the reaction intermediate a little bit lower in potential energy value. If you lower the activation energy barrier, more molecules are able to go over the hump. So it's just like if you we're going to go to Disney World for a day and the ticket's like $150. So not as many people can go in. But if you lower the price of admission, all of a sudden maybe it's half price day and so it's only $75 to go into Disney World. Now more people are able to go into Disney World at the same time. And in the case of a reaction, more reactants are able to go through the reaction and form products at any given point in time because there's less of a barrier to get started with the reaction. With molecules, it's more about how fast they're moving. At a given temperature, if the particles are just moving kind of an average speed, maybe when they collide, they're not really colliding hard enough to get a reaction going. But by adding a catalyst, then they're able to have those kind of medium collisions and they're stabilized in the intermediate form, and they can go ahead and form products in the end, even at the same temperature. The catalyst speeds up the reaction by lowering the barrier to get the reaction going in the first place. So that's what a catalyst does. Then, sometimes it's catalyzed and sometimes it's not. You often see multiple humps, all right? So the multiple humps start getting into the steps of a mechanism. If a reaction just has one hump, it's just a one-step mechanism. If a reaction has two humps, like the blue line we see there, that means it's a two-step mechanism. If a reaction's profile has three humps, that would be a three-step mechanism. So one thing we're going to be also able to see from this stuff is the way we can think about the steps of a mechanism and relate it to these graphs. Just a little bit more on catalysts at first. We want to make sure we know catalysts themselves, they don't get used up in the reaction, they get spit out. In this picture, there's a reaction happening and the purple atoms on the bottom are just a plate of metal. Sometimes something as simple as just having a metal plate in the reaction container can serve as a catalyst because metals are really good at loaning their electrons out to the reactants to help stabilize that intermediate. So in this reaction, the reactants are up right above the piece of metal. So black means carbon atoms and white means hydrogen atoms here. So we've got hydrogen and then we've got this carbon-hydrogen molecule there. If they just happen to bounce into that metal plate, they'll stick to it temporarily, and that allows the two hydrogen atoms in the diatomic H2 to separate from each other while they're stuck to the plate, and then they can go find the other molecule and they can bond to it in that way. The metal plate is still there both before and after the reaction occurred, but the reactants have clearly, they've done some kind of bond formation, and now they are the products. But the metal plate is still there. It didn't get used up. Well, a couple more vocabulary words with catalysts. Homogeneous catalysts, they're in the same phase as the reactants, so maybe they're all dissolved in the same solution. Or maybe they're all in the gas phase together. So aqueous or gaseous, they're typically going to be your homogeneous catalysts because they're in the same phase, or you could think of them in the kind of the same state of matter as the reactants. Heterogeneous catalysts are different phases. So solids and metals, like we saw in the last picture, that would have represented a heterogeneous catalyst. Present a two-step mechanism. All right, so each hump is a step, so I'm just going to put a little note here. This is a two-step mechanism. It would say like step 1, blah, 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 step 2, blah, 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 just like we see above on the notes page as an example. Is each hump is a step in the mechanism. Each hump has its own activation energy. So I showed with my red arrows on the board activation energy. I'm going to add little activation energy arrows to this. So this change in energy right here, I'm going to call it AE for activation energy. I'll just put a little 1 after it because that's activation energy of step 1. And then step 2 also has an activation energy barrier to go from the intermediate to the top of its hill, which is called the transition state. This is called activation energy, and I could put a little number 2 after it. So the activation energy for step 2. Does one of those humps look a little taller than the other? Not the height of the peak overall, but just from start to the top of the hill. Which hill might be a little bit higher just to go over individually? The first step or the second step? Yeah, the second step. I wanted to find a bigger exaggeration of one, but it looks like in this picture the second step might be a little bit of a bigger hump to get over. That means in this mechanism, the second step is the slower step, and in this mechanism, the first step is a little bit faster. So if it's just a really small hill to go over, that means it's a fast step. This is where kinetics and mechanisms, rate and mechanisms come together in kinetics. The smaller the hump, the faster the step. The taller the hump, the slower the step. Each valley is called an intermediate. So there's our intermediate, whatever reactant, or not reactant, whatever species we could say is present in the middle, that would be our intermediate. It's represented there. So it's a low energy zone, valley in between the two humps. And then each peak is something called a transition state. The transition state is like a snapshot in the middle of the reaction taking place. They're usually not at all like stable molecules or anything. It would be like when the molecule is disjointed into a really weird way, when the molecule itself is being broken apart before it comes back together to form a product. That's what a transition state is. So a few things to get out of one of these graphs more than anything. The number of humps is the number of steps in the mechanism. If it's a two-step mechanism like the one we see on the page up above there, it has 2 humps. If it's a 3-step mechanism, it has 3 humps. The valleys are the reaction intermediate. So this reaction just has 1 intermediate. And the top of the hill are called transition states. And then finally highlighted there, the greater the activation energy barrier for each step, the slower that step takes place. So each step, back to the mechanisms themselves, each step is also referred to as an elementary reaction. The word elementary reaction means it's a single collision event. All right, maybe 2 particles collide, and that's the collision event. Or maybe 3 particles collide at the exact same time. That could be a collision event. But each step represents an individual collision event, because if the particles don't collide, they're not going to react. once you know their elementary reactions, there's a really easy way to get the rate law from it. For overall chemical reactions, we cannot just assume that they're elementary steps. So to find the rate law, we either have to have all those data tables we looked at a couple of days ago, or we have to look at natural log graphs and inverse graphs. But if they tell us that the reaction is an elementary reaction, or if we see the word step 1 or step 2 beside it, it's going to be really easy to write its rate law. I'm going to jump to a later slide and then come back to the next slide. Does anybody need more time on this particular slide? All right. So flip back to the front page of that notes page, if you need to be on the front page. But just out to the right side of that, if you have some room to the right side of that, this is our reaction we looked at a minute ago. We let some things cancel. We just determined our catalyst. We determined our intermediate. Because it says step 1 beside it, I can write a rate law for this reaction. And it's as easy as this. It's still rate equals K. Then you just write the products in the brackets, just like they appear. So it's Cl and O3. So you do the same format we've been doing rate laws, rate equals K, and then you just write the reactants in the brackets. I'm going to put a little 1 next to that since that's reaction 1, and I'll put a little 1 next to the K right there just because that's the first step of the reaction. For my second step, it's just as easy. I'll just say rate equals K, put a little 2 after it so I know I'm dealing with step 2. And then I'll just put ClO times O. Neither of these, well, one of them may or may not be, but we can't say that this is the overall rate law for the real reaction. Remember, the real reaction was the one at the bottom where we added the 2 together and we got our final reaction. So these are rate laws for the individual elementary steps, and on Monday we'll talk about how do we relate that to the overall reaction's real rate law at the bottom. But if it's an elementary step, all you have to do is write rate equals K and then put the reactants in the brackets. Leave the products out of these things. Yeah?
Do you ever have to put the state of matter?
No, I never really see that in there. I think by putting it in brackets, we're talking about the molarity of them. Even if they're gases, you can still have molarity of gases. So that's a good question. We never really put the state of matter in those things. So that's what these charts are about that are on your notes page. Again, I thought I would skip and see a specific example first. And now we can see for any elementary reaction, jump.
So on that, the last part, are there just no exponents? Like we don't need to worry about putting it after
You don't need to worry about exponents in those particular reactions. If you had one, and that's what this chart's going to be about, what if one of those reactions had been this, 2NO, actually let's just do this, 2NO yields 2O4. So if this had been a step, then as an elementary reaction, then it becomes rate equals K. It would be NO times NO, which is the same thing as NO squared. And that's what they're showing us in symbol form on this chart. If the reaction had been A plus A, that would be like, say, 2NO, then it would be rate equals A squared. So I'm glad you asked that. If you have a coefficient in an elementary step, you don't have that too often, but if you have a coefficient in the elementary step, in a way, it kind of becomes the exponents there. Most of the time, it's going to be either just one thing by itself or 2 different things coming together. So there's some words for this. If a reaction is unimolecular, again, each elementary step refers to a single collision event. Well, if there's just one molecule in the one molecule in the reactant, like if it looks like this, something like this were taking place as our elementary reaction. There's nothing for it to collide with. We call that unimolecular. There's just one reactant. That means one reactant must be like just breaking apart on its own without having to have any collision. Most reactions are going to be bimolecular. That means two reactants. That means two reactants actually collide with each other in a single collision event. Occasionally, it would be rare because it would be unusual. What if three particles suddenly collided with each other at the exact place and time? That could happen. It would be rare because three particles aren't likely to be at the same place at the same time. But that would be called termolecular. And all of these have their own version of individual elementary rate laws. If it's unimolecular, it's just rate equals K times the reactant. If it's bimolecular, it's rate equals K, reactant times reactant. It happens to be the same reactant, would just be A squared. And then termolecular, again, you're just multiplying the three reactants times each other. It could end up looking like A cubed or A squared times B if you've got two or maybe even three particles of the same reactant. So the general word that we use is molecularity. So if I say, what's the molecularity of this elementary reaction, we would have to say it's unimolecular because there's just one reactant. If there's two reactants, like in the example we just did together with the Cl and the O, those were both bimolecular elementary steps. And most elementary steps are going to be bimolecular. All right, we just want to keep in mind, we can predict the rate law of elementary steps just by multiplying the reactants times each other in the rate equals K, this times that format. But most reactions are not simple elementary reactions. They take place through a series of steps. So we're going to think about the overall reaction more on Monday. Today we can just look at these elementary reactions. Some vocabulary words that go with that. I think this is what was on your printout. Unimolecular, a single particle breaks apart or rearranges itself. Bimolecular, two particles are colliding with each other. And termolecular, three particles happen to collide with each other. Again, that would be like three cars in a parking lot suddenly colliding at the exact place and time. Probably doesn't happen, but it happens every once in a while. All right, and we've written our steps for that. That actually takes us to the end. Can anybody think of any questions you have at this point? Yeah.
So when we're looking at these reaction graphs, does the steepness of the graph have any impact on time?
No, it's more about that from wherever you're starting to the top of the upcoming hill. That's what you want to focus on. The higher hills are probably going to look steeper, but these don't have a consistent x-axis. Usually the x-axis on these is going to be as the reaction proceeds. So we don't have to worry about finding the slope on any of these graphs or anything. Yeah, think more about these in terms of their shape. Probably the steeper the curve, the slower that step takes place actually, because it's going to be a higher hill if it's steep. But they don't have an x-axis that's to scale.
Okay. Like I would expect it to be quicker if it was just like super quick.
On these, focus more on the energy part of the y-axis instead of that. Because normally we do think of steep slopes as fast, right? But because these are about the energy that it requires to get through a step, not with regard to time, but just with regard to how much energy it takes. It's probably going to be the reverse of that, where steeper probably equates a taller hill to go over. So you can think of it more like if you were like trail running or something, a steep hill to climb over would actually take a long time to get over because it takes a lot of energy. You really have to slow down. All right, so what you're doing on these, you're going to look at some of these graphs, count the humps. Writing rate law for elementary reactions. And the very last one, kind of like yesterday's homework too, the last one's more of a particle diagram.